In this video, we'll be looking at the effect of the degree on a polynomial, how it affects the way the function looks, how it affects the end behaviors, and then we'll do some sketching of polynomials when they're in factor form, and we'll take a little sneak peek at the factor theorem and remainder theorem. So a big day today. And we're going to start off with some observations on how the degree of a polynomial and its leading coefficient affects a polynomial. So how are the end behaviors affected, the zeros, the turning points. Okay, so in terms of end behaviors talk about the direction that a function is heading towards as we look to the left and towards the right. So for end behaviors, the way we describe them is as x approaches negative infinity, meaning as we look long term to the left, what is happening to y? Is y going to positive infinity or negative infinity? So let's actually look at this first example. As I follow my functions towards the left, so as x is smaller and smaller, what's happening to y? It's going down forever. So this one would say as x approaches negative infinity, y approaches negative infinity as well, as can be seen right here. And as x approaches positive infinity, so as we go to the right forever, what's happening to the function? Well, it looks like it's going up forever. So as x approaches infinity, y approaches infinity as well. So when we're doing our end behaviors, we have two sides, the negative and the positive infinity of x. And we talk about what y is approaching. So these first two functions that we have, they are odd degrees. So this one here, factored form, 1 plus 1 plus 1. This is a degree of 3. And we have these opposing end behaviors. The next one, our degree is 1 plus 2 plus 2. It's also odd degree. And again, we have these opposing end behaviors. Now, I did say I want to look at the leading coefficient as well. The leading coefficient of the first function is this invisible 1 out front. And the leading coefficient of the second is this positive, a half. So we have a positive leading coefficient and an odd degree. The function is heading in opposite directions, but it has this overall upwards trend. We're starting from quadrant 3 and we're heading upwards to quadrant 1 in both examples. Now, in terms of turning points are, if you're following the path of your function, where you switch directions. So I have a turning point right here because at first I'm increasing and then I decrease. Now I'm decreasing and then boom, I have a turning point and then I increase again. So this first function here has two turning points. The next one, I'm increasing, then I turn. I decrease, then I turn. I increase, I turn. I decrease, I turn, and then I increase the rest of the way. This one has 4 turning points. So the maximum number of turning points that a function can have is always going to be 1 less than the degree. This was a degree of 3, 2 turning points. Degree of 5, 4 turning points. And the thing is, with odd degree functions, they can have 0 turning points. You could have something just like this going upwards. That's actually your most basic cubic function. And in terms of zeros, you could have up to whatever your degree is, number of zeros. So if we look at this example, 0, 0, 0, there's 3 of them. It was a degree of 3. Okay, this other one is probably going to have less, 1, 2, 3, even though it was a degree of 5. So it has less than its degree. But a odd degree polynomial has to have at least 1 x-intercept because we have these opposing end behaviors. Okay, that was a lot there. Let's look at more odd degree polynomials, but this time the leading coefficient will be negative. So let's take a look here. We have a degree of 2 plus 3 is 5, And a degree of 1 plus 2 plus 2 is also 5. But this time, we have these negative signs out front. And if you look at your end behavior, again, you have opposing end behaviors. However, this time, you're starting in the positives in quadrant 2, having this overall downwards trend towards quadrant 4. So this time, as x approaches negative infinity, we're going to positive infinity. We're going upwards on the left side of our graph. And on the right side, we're going down. Okay, so that degree and the positive or negative of the leading coefficient is going to tell you the long-term behavior. In terms of max turning points and zeros, it's going to be the same connection as before. For these degree 5 polynomials, I would expect a maximum number of turning points to be 4. Okay, there could be 0, there could be 2, but no more. Okay, and in terms of the zeros, I'd expect the maximum number of zeros to be 5. And I could have 4, 3, 2, 1. I need at least 1 0 though, because I need to have those opposing end behaviors, which means I need to cross the x-axis at least one time. Okay, so in terms of the turning points, we need to have an even number of turning points. We need to have an even number. So for example, 1, 2. If I made it more interesting, 1, 2, 3, 4. Like it's always going to have to be an even number of turning points in order to have those opposing end behaviors. Whereas for zeros, it could be from 1 to the maximum, so to the degree value of zeros. Okay, so that's the odd polynomial observations. Let's look at the even degree, and we're going to start with a positive leading coefficient. First of all, we should see that the end behaviors both going upwards to infinity. So as x approaches positive or negative infinity, y approaches infinity. In terms of the turning points, let's see. I have 1, 2, 3, and my degree was 1, 2, 3, 4. So that's 1 less. For the next one, I have 1, 2, 3, 4, 5 turning points, and my degree was 1, 2, 3, 4, 5, 6. And I had 5 turning points. So again, same connection. The max number of turning points is the degree minus 1. But I do need at least 1 turning point because this function needs to turn around so that the end behaviors go in the same direction. So for example, something like this. The parabola is the most basic even degree polynomial. I need 1 turning point to go back to where I started. In terms of the zeros, if I have a degree of 4, I could have up to 4 x-intercepts like we do in this example. If you zoom in a lot, 1, 2, 3, 4. I could actually have 0 x-intercepts in a even degree polynomial because imagine this was my x-axis. My polynomial could be all above the x-axis or fully below the x-axis because the end behaviors point in the same direction, so I never have to cross the x-axis. Okay. And if we have there's a typo here, my apologies, that should say even. If we have an even degree polynomial with a negative leading coefficient, we have downwards end behavior. So as x approaches negative or positive infinity, y is approaching negative infinity. And the turning points and zeros, same connection as the other one. So let's just check out our degree. 3 plus 1, degree of 4 here. So I'd expect a maximum number of turning points to be 3, and I need at least 1. So my options are 3 or 1. For the other one, our degree is 2, 3, it's also 4. So for turning points, it could be 3 or 1. For zeros, we could have 4, 3, 2, 1. I could even have 0 zeros. Okay. So now let's take these observations and make some predictions about end behaviors, turning points, and zeros. So for my first function here, my degree is 7. We're looking at this term right here. And the leading coefficient is negative. So we have an odd degree with a negative leading coefficient. So I'm expecting opposing end behaviors, and I'm expecting to start high and head overall downwards, which means for my end behaviors, I'm going to have as x approaches negative infinity, which is the left side, y approaches positive infinity. So we're showing this part right here. And as x approaches infinity, y approaches negative infinity. And that part I'm showing this. Now, for my turning points, I can have, this was a degree of 7, so I could have up to 6 turning points, but I could also have 4, 2, or I don't turn at all. Like it looks like a basic linear function. For my zeros, I could have 7, 6, 5, 4, 3, 2, 1. I need at least 1 0 because I do have to cross the x-axis because of those opposing end behaviors. Okay. Next one, don't automatically look at the first term. We have to look at the highest degree term, which is this one right here. The degree is 4, so we have an even degree polynomial, and the leading coefficient is positive. So in terms of my visual, very simplistic. I always, when I'm thinking of my visual for end behaviors, I draw the most basic even degree polynomial, which is a parabola. So I'm expecting everything to go upwards. So as x approaches negative infinity, y also approaches infinity. As x approaches positive infinity, so does y. In terms of turning points, it was a degree of 4, so I could have 3 or 1. So this is a 1 turning point. This would be 3 turning points. For zeros, I could have 4, 3, 2, 1, and I could even have 0. I don't actually know how many turning points, how many zeros I have. That's just, those are my options. When we actually start graphing, factored form is going to be very important to us. So we're actually going to make some observations here. And then we're going to get into some sketching. So in this first function here, I have a degree of 1, 2, 3. And I have a positive leading coefficient. So going from quadrant 3 to quadrant 1 makes sense. Let's take a look at our zeros. I have 1 0 at negative 5, 1 at negative 2, 1 at positive 4. And this actually fits beautifully with our brackets. Those brackets are going to give us the zeros. We set our brackets equal to 0, and we get the x-intercepts. Now, if you look at all of these x-intercepts, we just passed through the x-axis nicely. Let's look at the next one. We have a degree of 5, a positive leading coefficient again. So we have those opposing end behaviors, quadrant 3 to quadrant 1. In terms of the zeros, just going to zoom in a little bit here. We have 1 at negative 5. That matches here. If you took x plus 5 and set it equal to 0, be negative 5. We have negative 2, matches here. And we have positive 3. Now, if you look carefully at negative 5 and negative 2, their exponents are 2. And if you look at the behavior, I'm not passing through the x-axis, I am bouncing. So when we have an exponent on top of our bracket that is even, it's going to result in a bounce at that x-intercept. When it's an exponent of 1, we're just passing through. And finally, this last one, we have a degree of 5. Again, an odd degree. Negative leading coefficient, so I'm going from quadrant 2 to quadrant 4. Let's look at our zeros here. I have one of them at negative 1, which I would expect because I saw x plus 1, and it's a bounce because of that even exponent. But here at positive 4, I have an exponent of 3. So when you have an odd exponent on that factor besides a 1, this is called a point of inflection. And it's where the concavity changes. So if you look at this function, it starts off, it kind of looks like a parabola opening up. And then once I hit 4, it looks like a parabola opening down. There's this change in the concavity. Kind of looks like I'm taking a little pause on a step and then continuing downwards. So these observations are going to be very helpful for us to do a sketch of our polynomials in factored form. And that's what we're going to do right now. We're going to start with this one here. F of x is equal to 2x, x minus 3 squared, x plus 1 cubed, and x plus 5. First thing I'm going to do is identify my zeros. And I'll go the long way for this first one. You're just setting each factor equal to 0 and solving for x. So for 2x equals 0, when we divide both sides by 2, we get 0. For the other one, we bring the negative 3 over, becomes positive 3. Bring the 1 over, becomes negative 1. Bring the 5 over, becomes negative 5. And I'm going to look at the exponent of each factor. So the x was to the power of 1. This is a pass. The x minus 3 was to the power of 2. This is a bounce. X plus 1 is to the power of 3. It's a point of inflection. I'm just going to write pi. And the x plus 5 was a pass. If I want my y-intercept, I'm just going to evaluate f at 0. So set x equal to 0. And if I plug that in, well, I am just going to get 0. Like 2 times 0 times 0 minus 3 squared times 0 plus 1 cubed times 0 plus 5 is 0. And plus, that was one of my x-intercepts, so that is a common point. In terms of the end behaviors, let's look at our degree. I have 1 plus 2 plus 3 plus invisible 1 here is 7, so it's odd degree. The leading coefficient is positive, so I expect this overall upwards trend. So I'm going to go from quadrant 3 to quadrant 1. This is now enough information for me to do a rough sketch. So let's see. I need to go to negative 5, 2, 4, 5, so negative 5. I have one at negative 1, 1, 2, 3. Okay, so I'm going to plot my x-intercepts. Negative 5 is a pass. Negative 1 is a point of inflection. Positive 3 is a bounce. And 0, 0 is a pass. And I should be starting in quadrant 3. So, very rough. I'm going to go up. I'm going to come down, and I'm going to do that change in concavity. Then I need to somehow get to that origin, so I'm going to turn around, pass through. Then I have to turn around to get to that bounce. And I'm going to bounce off and add arrows at the end. Now, in terms of these turning points here, I don't actually know where they are, those local max and mins. If you're taking calculus later on, you will find how to solve for them accurately. We don't really care at this point. If you really wanted to get a rough estimate, you could average your zeros and find those points like you would in grade 10. It's not going to be the correct value. It'll just give you a general idea. So whenever I'm sketching, I just try to draw my turning point somewhere halfway between the zeros so it doesn't look too off. But in terms of where I should place those values with reference to the y-axis, it's just a sketch. That's why you'll see I didn't even label my y-axis. Okay. Let's try one more. This one's going to be a little fancier. So I have that negative 3. It's not attached to an x, so no x-intercept from there. For this 2x plus 5 bracket, just be careful. The x-intercept is not negative 5. If you bring the 5 over, it's negative 5, but then you have to divide out the 2. So negative 5 over 2. For the 2x plus 1, it's negative 1 over 2. Then we have 3, 0, and 7, 0. The first bracket was a bounce because of the exponent of 2. The next one is a point of inflection. because of the cube. Then we have a pass and one more bounce at the end. In terms of the y-intercept, I'm going to sub in 0 for my x's. And I get to 11,025. So don't freak out if your y-intercept is a little outrageous. In terms of the end behaviors, I already see a negative leading coefficient. My degree is 2 plus 3 plus invisible 1 plus 2. So 5, 6, 7, 8. So it's even with a negative leading coefficient. So I'm expecting downwards end behavior. So as x approaches negative and positive infinity, y is going to negative infinity. So with that in mind, let's get into a very rough sketch here. So 1, 2, 3, 4, 5, 6, 7, and I need 3. 1, 3, 3, 2, 1. Okay, in terms of my x-intercepts, negative 5 over 2, which is negative 2.5, and that's a bounce. Negative a half, so negative 0.5 is a point of inflection. 3 is a pass, and 7 is a bounce. And my end behavior should go something like this. I'm just going to put a note. I'll erase them later because they're probably a little bit off. My y-intercept is somewhere very high here, and I'll label that in after I do my sketch. So I'm going to start, and I'm going to bounce off. Then roughly halfway, I'm going to turn around and do a point of inflection. So kind of changing that concavity. I'm going to head upwards. Then I have to dip back down, and I'm going to pass through 3. Then somewhere between 3 and 7, I need to turn around and then bounce off of 7. And there we are. Pretty good. And this will just get labeled with that y-intercept. And there's my sketch. Okay, so that's us taking all of our observations about polynomial functions and applying them to our sketches. So now that we have that, and please remember, you could always pause these videos and then go get more detail in the D2L lessons. This is just kind of a little preview of everything that you will see in D2L. Obviously with math, we need to do practice to get a skill. Okay, so now that we have the sketching, now we can do the opposite. I'll give you a sketch, or I'll give you information about the polynomial, and you come up with the equation. So in this example, I've given you the visual of the polynomial, but I could also give you the same information in words. And what is important here is I have a 0 at negative 4, at negative 2, which is a bounce, and at 2, which is a point of inflection. That's already telling me a lot. The passive negative 4 means I should have an x plus 4 bracket. The bounce at negative 2, I should have an x plus 2 bracket squared. The point of inflection at 2 should be x minus 2, and that'll be cubed. I don't know the leading coefficient, so I'm just going to put an a value. Okay? And now, if I know a point on this function, I can sub it in and then solve for a. And we do. We have this nice y-intercept. So I'm going to replace x with 0, y with negative 8. And now I'm going to clean up. So negative 8 equals a. 0 plus 4 is 4. 0 plus 2 is 2. Squared is 4. 0 minus 2 is negative 2. Cubed is negative 8. And now 4 times 4 times negative 8 is negative 128 times 8. And then I'll divide both sides by negative 128. And we get an a value of 1 over 16. So our final function is y equals 1 over 16 times x plus 4 times x plus 2 squared times x minus 2 cubed. Now, these zeros were really nice, so when we put them into the factored form, it was just the opposite sign. But just a little note, let's say your 0 was 3 over 2 comma 0. You can try to find it. If you can't just see it, you could say, okay, x equals 3 over 2. What would I do to get everything back to one side, because you should not have fractions in your factored form. So first thing I would do is cross multiply. So 2 times x equals 3, and then bring the 3 over. This would be my bracket, 2x minus 3. Likewise, if my 0 is negative 5 over 2, my bracket would be 2x plus 5. 2, because I need to divide by 2, so I'm going to make that the coefficient. And then this was negative 5, so I put the opposite sign. So you could do a little bit of a visual way, you could do an algebraic way, but make sure your factored form never has fractions.